Okay, here's a quick one, fluid dynamics. Fluid dynamics just means that the fluid is in motion. And basically, we categorize the motion of a fluid in terms of a steady flow, what we call streamline or laminar flow. This is where every particle that passes a particular point goes through the exact same trajectory as every other particle, okay? Um, with streamline, the streams cannot cross one another, and basically, it is what we would consider to be a steady state. It does not change with time. So a streamline flow, just as the name implies, indicates that all the fluid is flowing in a constant stream. And you can see that effect right here. Here is a car undergoing a drag test. They're trying to look at, how the fluid flows around the car itself to try to maximize the fuel economy. Turbulent flow, as the name implies, indicates that we are not in a steady state anymore. As we get the fluid going fast enough, and as we have enough internal friction in the fluid, we start seeing these eddy currents show up. And here's a blade passing through a candle. This one's called this is a Schlieren photograph. It's very sensitive to any changes in density. And you can see as this blade from a fan passes by, there is this clear vortex on both sides of the blade, which sets up. So turbulent flow is usually happens when the fluid gets going so fast, it can no longer maintain the streamlines, and the internal viscosity of the fluid generates some of these. Now we're going to talk a lot about ideal fluids. Um, Ideal fluids are just like, you may have studied ideal gases, and we'll study ideal gases later on, are a simplification of a real world problem where we take out some things. So, let's take a look at what's going on right here. First of all, we remove viscosity. So we're not going to have the possibility of turbulence. Turbulence is generated by the internal viscosity of the fluid. Also, going to say that even though real fluids can be compressed, we're going to treat the fluid as incompressible, which is pretty close to being true for liquids. Fluid's going to be have a steady state motion, so it's going to be all streamlined. And again, as we said, without viscosity, we're not going to get turbulence. So that is going to be the ideal fluid. And that's going to be important for when we start talking about things like Bernoulli's equation later on. Now, if it's incompressible, the total volume of the fluid must be constant. So again, thinking about volume, if we look at these little cylinders, let's say we go from a pipe where the radius is smaller, then we go to a larger radius. We can't change the volume of the fluid because it's incompressible. That means that the volume of the fluid at point 1 is going to be the same as the volume of the fluid at point 2. This equation of continuity produces a fairly intuitive result. It means that when we send the fluid through a smaller pipe, it's going to have to flow faster to keep the same volume going through there. So at A1, the volume is going to be greater because the cross-sectional area is less. At A2, however, we've now decreased the cross-sectional area, so the fluid doesn't have to go as quickly, so V2 is going to be less. So again, completely intuitive. You send water through a small pipe into a large pipe, the fluid's going to slow down. Okay, essentially, we keep the volume constant. Again, it's incompressible. This is sort of a neat demonstration that you can do. Watch the water coming from the sink. Now, we treat the water as though it's in free fall. When it first comes out of the tap, it's traveling basically nearly zero. Not at zero because it is flowing. Notice what happens. The cross-sectional area is getting smaller and smaller and smaller. Why? Because the fluid is accelerating as it falls. Again, it's incompressible or nearly incompressible. So when it's going slower, it has to occupy a larger cross-sectional area to maintain that volume. As it picks up speed, that cross-sectional area becomes less and less. Again, this is just free fall. Nothing really complicated going on here.